Now in a previous video, we calculated the area bound by a function and the x-axis from an a to a b value, or a lower bound to an upper bound. We can get more complicated than that, okay? Things never stop in VCE methods. Things never stop getting more complicated in VCE methods, and it's an unfortunate fact of VCE, and specifically VCE methods. They try and make everything as hard as possible, and they try and add all these layers of complexity. But luckily, I'm here to help you try and solve this one. In this case, we're trying to find the area that's stacked between two functions. So in this case, we have f of x is equal to x squared, we have g of x is equal to x, and the shaded area, which is this black area here, is what we're asked to try and find. Now, if you want to make this really easy for yourself, you can memorize this formula, but it's really important to understand where the formula actually comes from as well. Because I'm a big believer in the fact that if you understand where something comes from and you understand the derivation, then it makes things a lot easier to actually apply. And it makes things a lot easier to remember as well, because you can think about where the formula is actually derived from, and you can kind of get that formula back for yourself. And this is a specific thing and a very niche idea that's actually not on the formula sheet, because this is kind of an application or an extension of what we know, which is area underneath the graph. So these types of things don't really have formulas in the formula sheet. So something that you have to kind of practice and also memorize at the same time. So let's get started with this one. The area in between two functions, just simply put, is the top function, or the integral of the top function minus the bottom function from the lower bound to the upper bound. And there's some things that we have to understand about this formula specifically. I mean, this is pretty obvious, but what is the top function and the bottom function? In this case, for this shaded area, g of x is equal to x, or that linear equation, is the top function. The red curve is the top function because it is physically stacked above the other one, which is f of x is equal to x squared. But just keep in mind that this is not kind of a cookie cutter approach, because you might have some other examples where you have some portion of the graph where one function is above, but then other portions of the graph, or the area, where the other function is above. So in that case, you have to split it up into two integrals the same way that we did if you had area above or below the x-axis. So you have to kind of split up the calculation into multiple areas. Don't worry about that yet. We'll do another example after this one. Now, easy. X is the top function, g of x is equal to x is the top function, the red, and then the bottom function is f of x is equal to x squared. But where exactly do we integrate from? What is the lower bound? What is the upper bound? That is something that we have to find through algebra. So in this case, what we do is we just find the intersections between the curve x and x squared. So we say x is equal to x squared minus x is equal to 0, x outside of x minus 1 is equal to 0, x is equal to 0 or 1. Cool. So it goes from x equals 0 up to x equals 1. So we have to find the y coordinates. No, because we don't need them when we integrate. So what we do is we say the area is equal to the integral from 0 to 1 of our top function, which is the red curve x, minus the bottom function, which is the green curve x squared. So we've got the integral from 0 to 1 of x minus x squared. And this is pretty easy to calculate. Pretty easy integrals here. X becomes x squared over 2. X squared becomes x cubed over 3. I expect you guys to kind of know where these integrals are coming from just by applying the formulas. I'm just going to rush it in this case it's not really the point of the exercise to practice the integrals, it's more so just understanding the concepts. Now substituting 1 and 0, this is the luckiest case because it's super easy to substitute in. 1 squared over 2 is obviously just 1/2, 1 cubed over 3 is 1/3, and then everything becomes 0 when you substitute in 0 into it. 1/2 minus 1/3 is just 1/6 if you convert it into its lowest common denominator. So we've got 1 over 6 units squared, and you might be thinking that is a super tiny area, 0.16666 reoccurring, or just 1/6 if you want to put it simply. Now it's a really small area, by the way, but the reason why it's so small is because this graph is so enlarged. So this coordinate here would be 1, 1. This coordinate here would be 0, 0. So this is a really small sliver of that portion of area. So that's why the value is so small. Now we'll go into a more complicated example where we have multiple portions of our area that we need to split up into different integrals. Okay, so here we are with a pretty complicated example. We have the area that's bound or stacked by f of x is equal to sine of x and g of x is equal to cos of x. So we're trying to find that black shaded area. You can see from kind of x equals 0, the y-axis, to that intersection there, the red curve is above the blue curve. But then from that intersection to the second intersection, we have the blue curve above the red curve. So that's how we split our area or our integral equation up. We have that portion, that's where the red curve is stacked above the blue curve, and then the second portion is where the blue curve is stacked above the red curve. So the first thing we have to do is figure out where those bounds are for each of those integrals. And the only way that we can do that is by solving f of x is equal to g of x and finding those intersections. So in this case, f of x is equal to sine and g of x is equal to cos. So we just say sine of x is equal to cos of x. And you can kind of see that this is for one cycle, and yeah, we can just solve this when 0 is less than or equal to x, which is less than or equal to 2 pi, or pretty much just the first rotation or the first revolution of these circular functions. Now, a lot of people see this and get kind of confused. Oh, I've got a sine, I've got a cos, what do I do? You just divide both sides by cos, because what that'll do is you get sine over cos on the left side, which becomes tan, and then you get cos over cos on the right side, which obviously just becomes 1, because they cancel out with each other. So what we're doing is we're just solving tan of x is equal to 1 for the first cycle. Now you can go through the whole rigmarole and try and solve it. I'll just tell you that the solutions are in the first and the third quadrant, because that's where tan is positive, and they're just going to be pi on 4 and 5 pi on 4. You can do the long way if you want, but for this question, the point of it isn't not the trigonometric solving, it's actually applying our area between two curves kind of formulas and our concepts. So you can see this part is going to be pi on 4, this value here is going to be 5 pi on 4, and that is obviously x is equal to 0. So I'm just going to write them in. So this is pi on 4. I'm going to break my rule and not put the coordinates because they do not matter in this case. It's kind of just more for our reference. Sweet. So what we're going to do is split it up into two areas. We've got, maybe we'll call this one A1, this one A2. So A1 is going to equal the red curve minus the blue curve, so sine minus cos. So the integral of that, sine minus cos dx. Now what are our bounds? Lower bound is 0, upper bound is pi on 4. Pi on 4, sweet. A2 is going to equal the blue curve minus the red curve. I think I actually got that one the wrong way around. Oh, cooked it a bit. Yep, okay. So cook that one, cos of x minus sine of x, because it is the red curve minus the blue curve for the first portion. The other one is going to equal the blue curve minus the red curve, which is sine minus cos dx. And this one is going to be from pi on 4 to 5 pi on 4 as our lower to upper bound. Now we can evaluate all these, so we can just say the total area is going to be equal to A1 plus A2. So A total is going to equal the integral of cos minus sine. So integral of cos is sine. Integral of sine is negative cos, so we're minusing negative cos, which becomes a positive cos. It's going to be plus cos of x, and that's from 0 to pi on 4. Now our other integral, sine, integral of sine, what's that? That becomes negative cos. And integral of cos, that becomes positive sine, but we're minusing it, so it becomes negative sine of x when we do our final calculation. That's from pi on 4 to 5 pi on 4. Hopefully this is still in view. I think it is. Now, you can see that this one is fully negative, so what I can do is just remove the negatives, make that positive, and I could also swap my bounds as well. So make the top bound pi on 4, try and get it as efficient as possible, just rubbing out the 5, and I'll add a 5 to the bottom one. Again, getting rid of the negatives is a life changer. Now, let's just do our substitutions. Now, sine of x, when we substitute in pi on 4, sine of pi on 4 is just root 2 on 2. I can write as 1 over root 2 as well, but I prefer to keep it rationalized. Cos of pi on 4 is actually the same, root 2 on 2. And then our minus sine of 0, which is 0, plus cos of 0, which is actually 1. Don't get this cos of 0 is equal to 0. A lot of people do that. A lot of my students do that, and it's because they just see, okay, cos of 0, it's going to be 0. Cos of 0 is actually 1, because it's the x value when the angle is 0 on the unit circle. Now, cos plus sine of x for pi on 4, it's exactly the same as this substitution here. So that was root 2 on 2 plus root 2 on 2. Now, we minus the substitution of 5 pi on 4. This is where it gets a bit more confusing. So I'm just going to draw the unit circle. 5 pi on 4 is in the third quadrant. And actually in the third quadrant, both sine and cos are both negative. So what's actually going to happen here is we're going to have negative root 2 on 2, because when we simplify that angle, it ends up becoming pi on 4. So it'd be minus root 2 on 2 minus root 2 on 2. Now I like the sign of this because we can see that there's a lot of square root of 2's, which makes it a lot easier to simplify. So square root of 2 on 2 plus square root of 2 on 2 is equal to just square root of 2 by itself. I'm just going to make this square root of 2. And it's the same for all these ones as well. Square root of 2. I'm going to use a different color actually. So this one becomes square root of 2. Oh my goodness, that's even worse. Square root of 2. square root of 2. Now we're minusing the same thing. We're minusing the minus of that, so the negatives cancel out. So this one will become square root of 2 as well. So that's really messy, but hopefully you guys can see that this one becomes square root of 2, and then negative of a negative square root of 2. So we end up having 3 square root of 2's minus 1. And that will be unit squared. Don't forget the unit squared for area, and that'll be our final area for this stacked integral. And you can see that this one is very messy, because whenever we have sines and coses, it always gets confusing, because sines become coses, coses become sine, and it just gets really messy because you have a lot of trigonometric terms and you have a lot of angles to substitute in. But hopefully you can see, if you break it down and get rid of the negatives, I really emphasize that, getting rid of the negatives. If you get rid of the negatives and break it all down into its components, it actually becomes a lot easier. And in this case, you have a lot of common terms that you can actually combine together. So you can see here, I try to keep everything in terms of a common denominator to make sure that, it makes it a lot easier to combine terms and substitute things in. And you can see here, if I just recognize that these are all the same brackets, it makes everything a lot easier in the long term.